When mathematics students at universities start into their first semester, they are usually presented with an introductory course about the basics of what they need for the rest of their mathematical career. And within those lessons lies an important technique to be developed throughout the first semester: how to write down formal mathematical proofs. Me and a bunch of my colleagues were struggling a lot with this back then, so I want to give you an introductory lesson on how to prove anything. The subject of a proof is a certain statement which can be true or false. There are two important types of statements to prove: ones that say something about all objects of some type, and the ones that only say something about at least one object of a given type. Here are two examples. All prime numbers are odd. A whole number smaller than 0 exists. Now, aside from the fact that the first statement is false, we notice that it provides a statement about all elements of a certain type, in this case prime numbers. We denote these kinds of statements with this upside down A here. The second statement, however, gives us some information about at least one element. There might be multiple, but there must always be at least one, which is usually denoted by this mirrored E. Now, to create meaningful statements out of these types, we need logical as well as set theoretical operators. In our starting inventory, we only have 3 of these. This one is called AND, combines 2 statements and evaluates a true if and only if both of the statements are true. The next one is called OR and is quite similar, but evaluates a true if and only if at least one of the statements is true. Why am I putting so much emphasis on the if and only if, you may ask? Well, that's because you will hear this a lot when doing any kind of research on mathematical topics, and it just means that the relationship described works both ways, as we notice in the previous usages of the phrase. If statements A and B are both true, then A and B is also true. But this also works the other way around. And to get started, we will also need one set theoretical operator called the in or element of operator. A set is what we just call a collection of things, and we can use this operator to explain the relationship between an element and a set of certain elements. For example, we could say that the number 5 is in the set of whole numbers, usually denoted by this fancy Z here. With these 3 operators in our pocket, we could now also go on to define more advanced operators. An intersection, for example, is an operator that's very easy to understand visually, but with the tools at our disposal, we could formalize it a bit. For example, we could say that the intersection of 2 sets A and B is a set containing only elements X that are element of A and element of B. You may notice 2 things about this definition. The first being the structure of everything. The curly braces used to denote a set definition, the declaration of our variable X here, and the condition section for the X to be included in our set. The second thing is the abundance of very short and undescriptive names everywhere. Even if you may notice the naming scheme of using capital letters for sets, you may still ask yourself what X, A or B even mean. These are all variables that can basically be anything you want, so it's good practice to insert something into these definitions to make sense of them. For example, if you substitute the sets A and B for colors and fruits, you know one of the elements is gonna be orange. The reason I put so much emphasis earlier on the if and only if phrasing is that a lot of statements are merely just implications or conditionals, which are kinda similar but only work one way. They consist of 2 arguments, the first of which we will call the condition and the second the result. An example would be if 2 natural numbers are odd, their sum is even. If we reverse this statement, it becomes false, with 2 and 4 being an easy counterexample. Also, something to note is that we don't care about even numbers when trying to check whether or not our statement is true. This may seem very obvious, but it's an important detail when approaching how to prove an implication. Let's analyze this last part with some information from earlier. The statement we used here actually concerns all natural numbers, which is why we could use a counterexample to disprove it. Using numbers like 2 and 4 to fulfill our condition of the sum being an even number, and then using these numbers we show that at least one of them, or in this case both, are not odd numbers. Proving an implication about all objects is a bit more tricky, but something any math student will have to do quite often, and it is therefore also quite important. To do this, we need to assume the condition of an implication is true, namely that we have two numbers which are odd. Let's just call them x and y, and then prove the result, namely that their sum is even. To show this, we know that any odd number can be expressed by an even number plus 1. So we can express x as x even plus 1 and y as y even plus 1. Again, if all these symbols or nondescript variables are confusing you, replace them with some meaningful substitutions, like 5 for x, meaning x even becomes 4, to make sense of everything. With this we can express the sum of x and y as a sum of two even numbers plus 2, which is then even. This proof of course depends on the knowledge that the sum of two even numbers is even, but you will quickly notice that in maths, any proof depends on some given knowledge before it. And at some point down the line you will just have to make assumptions about the existence of numbers. But that's a topic for another video. A neat trick when trying to prove an implication is something called proof by contradiction, which can often be easier than proving a statement directly. We know that either a statement or its negation must be true, and an implication is false if and only if the result is false, but the condition is true. We can use this knowledge and show that if the result is false, the condition must also be false, and from there we follow that the statement must be true. If you didn't quite get that, don't worry, it will be way easier with an example. Suppose we want to prove the following statement. Let's use n as our variable for a whole number. If 2 to the power of n is greater than n squared, then n is greater or equal than 0. To use the proof by contradiction method, we assume the negation of the implication. So n shall now be a negative number. If that is the case, then 2 to the power of n is a fraction, but n squared is still just a positive number, meaning 2 to the power of n is smaller than n squared. And since this is a direct contradiction to our condition, we have now proven that this isn't possible and that the statement is therefore true. Now, if you're someone starting with your mathematics studies at university and you find yourself struggling with proving stuff for the exercises, I would recommend practicing formalizing logical statements. That is, taking natural language statements and writing them down using quantas and logical operators so you have something concrete to work with afterwards. And once that's no longer an issue, make sure you have a methodical approach to solving those formal logical statements. If you have to prove something for all elements, don't be overwhelmed and just start with the methodical approach of choosing an arbitrary one and think about its properties and what you can conclude from those. Even if a problem seems very unsolvable, approach it formally and then check the tools at your disposal. Alright, once again, thank you so much for watching. I'm not sure if this video will do too well, but I thought it's a very important topic that I noticed many people, including myself, struggling at the beginning of their university studies. As always, there's more interesting topics coming in the future, so I would greatly appreciate it if you could support me by subscribing to the channel. Thank you and see you.